So imagine this fantastic day where you go outside. The sun is there, shining like never, and you see this unrealistic blue sky, like you see only in Disney's movie, you know? You imagine this? You feel something new, something that there's something. And so you get back, you look around, you see all those families and children playing together. Not so far, you see this little boy, about 5 or 7 years old, you know? And he's looking in the sky with his big, bright, open eyes and said, "Is that? Oh, look at it! It's a bird!" And you see that laughing and tell his son, "Oh, son, it's not a bird, it's a plane." And the son replied, "Oh, I don't think so. It's look more than only a plane." And it's there. You realize that you're not the only one that feels the way you feel, you know, the happy, successful, and free. You should say, "Oh, Victor, come back to reality. What are you talking about?" I will tell you, because how can a plane do this feeling to everybody? I will answer. In fact, the challenge we give us is not very complicated. It's quite simple. We have to design or to imagine an aircraft able to travel with three containers from Montreal to London, and with economic and ecological advantages. We saw there the opportunities to do something more than only a plane. In fact, it's about a philosophy of mixing knowledge and technologies like morphing wing, virtual cockpit,
CMC, École Nationale,
and real time, you know, with passionate people to do economic and ecological innovations. Ladies and gentlemen, my name is Victor, and I'm here with Juan Sebastian, Nicolas, and Jason Tan. We are from École Nationale Technique, and we imagine for you today the green cargo for the blue sky of tomorrow. I will get started to explain you how we begin, how we start the project. At first, we had two choices to create creation or optimization. I remember an old man gave me an advice. You have to start with something great if you want to do something fantastic. So we choose to optimize the most efficient airplane today on the market. We all call it C-Series. The C-Series have great innovation, you know, like optimized aerodynamic, the use of light material. There's also low need of maintenance, and the best, the first and principal reason the most important point of C-Series was that the dimensions are perfect to fit the cargo in it. So that's it. But now you should, like everybody knows, after a few years, our airplane is too old to fly. And we think about this. By using advanced material, C-Series give us the opportunities to optimize the efficiency of our cargo at the end of life. There's also some research that have been done by Aerospace Technology Center to help us to optimize reusable and recyclable component. It's about an eco-design philosophy. I mean, with bright and smart design and smart manufacturing. Like we manufacture we reduce the use of toxic material like chrome and lead and cadmium, you know, and it's that's it. But now you should want to know how we get how do we load this plane area. We have a concept of loading at the front. We do opening door at the front, and it's because if we don't need, it doesn't need a strong and powerful structure, because the nose is very light in comparison with other plane that the fuselage at the back, the tail boom open at the front is very light, so no structure. There is it. So we also do we also optimize the front of the nose to optimize the fuel consumption. And the cockpit. Where is the cockpit? We think about the cockpit at the back of the plane, a virtual cockpit. Like the technology are there. We can do it because it's the same way that CAE does it with the virtual simulator. We can do it this way, or in future, maybe autopilot can be also contemplate. Okay? Thank you.
Thank you, Victor. So now I'm going to talk about the materials that we will use in our plane. So they are mostly inspired by the C series. The tail and the nose are in composites, and the fuselage is in aluminum lithium alloy. With the high development of the additive manufacturing techniques, we think that by 2025 it will be a really reliable process for aerospace industry. As you can see, go back here, the General Electric Aviation has developed a fuel nose that's with a complex geometry simplified to only one 3D printing process. So it's an excellent way to reduce the cost of doing forging, castings, machines by only one process. We also reduce the need of tooling for castings, for example, and for forging. So we'll get more efficient processes from this technology. Another great innovation, and we can go search with this technology, are the metamaterials that are being developed at the Lawrence Livermore laboratory. Now, these materials are mostly made of plastics, ceramics, and metals, but the real innovation happens in a nano level. The microstructure of the parts will be made in a micro-lattice way, like you can see in the picture. So it will be very ultra stiff and ultra light, because it has unless there's less material in the parts. So how to manufacture? The composite parts will be continued to do in autoclaves and prepegs, because they are very reliable for industry. And the ATL to create high accuracy parts with high quality. And this, the projection microstereolithography is the process that is used by the Lawrence Livermore laboratory to create the metamaterials. It's the perfect way to 3D print really at a really small level. And this is the process that the General Electric Aviation uses to 3D print the complex geometry parts. It's called digital metal laser melting. So now moving on to the engine, we wanted to optimize it, get the most thrust with a lower consumption, because we want to go at high speed to minimize the depreciation of the goods, but without having to spend much money on fuel. So we opted for the turbo gear fan from the Pratt & Whitney Pure Power Technologies. It's an excellent way to increase the bypass ratio of the fan without having to add more compressor stages. So the technology happens between the fan and the low compressor stage. It's a gearbox that drives the fan at a lower speed, and it increases its aerodynamic performance by reducing its speed. Another advantage is that there's less noise because of its low speed, so we can create a lighter engine this way. Another great innovation that we will see in our engine will be the ceramic matrix composites. There's ceramic resin and silicon fibers. This material is very performant for the hot section of the engine, for example. It can resist to higher temperatures than the nickel alloys do today, and it's 3 times lighter. So it will not only reduce the weight of the engine, but it will also improve its performance, because today a lot of cooling is needed at the hot section. So now we can remove this cooling that's coming from the airflow and use it for thrust instead, adding more fuel consumption, reducing the fuel consumption. So thank you to all these game-changing technologies. We will reduce the consumption by 15%. This is what the clear turbofan of Pratt & Whitney offers, but we think that it will be more than that. So I'll pass the microphone to Nicolas.
Thank you. We already improved our engines to reach effectively our goals, that is, reducing the fuel consumption and optimizing the durability of the engines. Then, we asked pilots concerning important factors concerning the fuel consumption. And we realized something important. An aircraft draws on its power reserve more during takeoff than at any other time. Plus, it produces the most harmful emission at this step. So, we opt for a solution. It's called the École Nationale by Airbus. The concept is simple. This is a catapult. While on the runway takeoff, the aircraft could be maneuvered onto a track system and accelerated using electromagnetic motors built into the track or into the aircraft itself. This technology could need an important organization between all airports, of course. This is the reason why Airbus considers this technology available in more than 10 years. But as we are precursor with our concept, we propose to develop this technology in collaboration with Airbus. Accordingly, we plan to develop an universal type of pedestal to install all kinds of aircraft on the same catapult, depending the need of power. It could really revolutionize the way we take off. That definitely confirms this technology is the most adapted to our aircraft, because on our aircraft, the most concept is the eco-efficiency. On the same way, about the eco-efficiency, we developed another concept. The most thing we desire to eliminate during to realize our innovative concept is the waste of power. And the first aircraft waste of power is on the ground. So we choose to adapt the wheel tug technology. Wheel tug is an onboard system that moves aircraft on the ground using electric motors. The electric drive system, which uses high-performance electric motors, is installed in the nose of the aircraft. The motors are driven by electricity generated by the HAPI. You can type into the report more detail about this technology, but concerning our aircraft, there is an important fuel economy, a positive impact for the environment, and this is the easiest way to maneuver the aircraft. So, finally, our last innovation. To improve our concept, we chose to find an innovation about the wings to reduce drag, and reduce weight. At first, we thought a flying wing, but we didn't select it because of negative consequences of this design. First, the lack of space for the payload, and then the lack of conventional stabilizing surface and associated copper surface. That means your aircraft will be unstable and difficult to control. After investigation, we chose a new concept called the morphing wings to replace the classic flaps used on the wings mostly to reduce the speed during the takeoff and landing flights. The name of this concept is called the ALT. It's currently developed by the NASA and Sysplex associated with US Air Force and Gulfstream Aerospace. The main issue about the actual flap structure composed by mobile part and actuator is the aerodynamic profile breaking. With the ALT, it replaces moving part with shape-changing assembly, so it allows wings to bend and twist to maneuver flat into the air. So, these advantages are drag reduction means the fuel economy estimated around 10%, the airframe noise reduction is estimated around 40%, and the development of this technology is actually on test that prove the safe way of this technology. So, no, numbers are numbers. It's important in our society to define the value and viability of a concept. As you can see on the diagram and the tabs, accumulation of small improvement can make the difference. No will make the difference between actual action and realistic provision of the development of the aerospace industry. Our future doesn't need isolated work. So, this is not our solution, but this is yours, and I propose you this concept. And then, finally, for conclusion, our team is international. Colombian, French, Canadian, Chinese. We have all strengths and weakness, and we work together on this project. We really love this project, and I hope we will appreciate the solution for the future. We hope by this report to underline the importance of the international collaboration. And then we also thank Aeroportal about the possibility to express ourselves into this contest. And we thank all the professionals that got involved in this organization of this case of study. Thank you.
Because you named other sponsor of this event. So it's the time for the dragon now. For now, 10 minutes of questions for you. Good luck.
Can everyone hear me? Yeah. First of all, well done. Lots of energy and enthusiasm. École Nationale d'Aéronautique. I apologise for my French accent. You talked quite boldly about these efficiency gains you can get from different aspects of your design. You talked about a 5% gain from morphing wings, 5% gain from an optimised aerofoil. I'm not sure you mentioned at any point what your design cruise speed was. And I just wondered if you could expand on those two things and where you get these numbers of 5% for and how they relate to the design speed of your aircraft.
We use these numbers come from the website, for example, the CCB's program. We compare this to today's planes that are flying on the market. These are numbers that come from Pratt & Whitney engines and estimations that Airbus have done with the École, for example, and the NASA.
So why, I mean, one of the things you mentioned in the report is the option of variable sweep. Why would that be important for you?
For the marketing?
Yeah. I mean, in what sense? I mean, you talk about variable sweep in the report. Why is that important in the context of your design?
Can you repeat the question, please?
So why would having variable sweep on your wings be important for your particular aircraft?
Oh yeah, okay, sorry, thank you. So the morphing wings concept is developed currently by NASA, right? And then this is just changing the flaps on the wings. There is a lot of promises about this technology currently developed, but we took this safely. We choose just what exactly the flight test actually. And this improvement about the flaps is a reality because the numbers we get to you, the release date on the Sysflex website in NASA, and this is actual result of the flight test and the ground test.
I'll go next. Thank you very much for your presentation. Very interesting. I find your proposals for the catapult and the Wilton very interesting, very bold choices, morphing wings. It's all interesting. But what about the costs of development? We haven't been presented anything about costs.
Can go to the slides. We estimated a profit of 8,000 per flight, so it will give us 8 million per month to 96 million a year. But money is not the reason we are doing this. It will be the result of our work. We are doing this to improve our world, to get a creative and problem-solving skills. And we think that, yeah, we are risk takers, but I think that it is worth it because we want to see a better world with an eco-efficient airplane.
That's all nice. From a business standpoint, it doesn't fly very high. Any arguments? Anything you could?
Well, we choose technologies that are being developed today. So there's things they are doing testing. So we think that it will be just putting them together. We don't know the cost today.
Can I add something? Excuse me?
Yeah, sure.
Then you talk about Wiltog, okay? And then Wiltog is already installed on some aircraft on the Air Transat company, and it's actually give profit for this company. And then, for example, the EcoClimb is an expectation, okay? But as we are kind of realistic, this plane technically fly. There is it's safe. It's what I mean. And about all the technology we had on our plane, there is maybe, as Vladimir said earlier with the other group, new generation of our aircraft coming out. You know, it's not for the first aircraft, but we plan a life after the mission of our aircraft, and this is the way we think it. And I think in the aircraft history, all this improvement we have today, there is somebody think like that before to do it. So this is what I wanted to say.
See if this works. It does. I think you guys had a great presentation in terms of being able to come up with a grand entrance. You did a fantastic job with that, and being able to show us how the payloads were easily dropped into the fuselage. If it were that easy, it would be fantastic. The question that I have for you is really on the catapult side. Having worked on the F-18 and having seen the issues that the catapult can bring and whatnot, did you give some consideration in terms of what kind of extra structure you would need to be able to sustain the catapult?
Okay. So this concept of catapult currently developed by Airbus, sorry. They planned it in more than 10 years, as I say, because of the infrastructure of all the airport and everything. They have to have the proper runway to take off this technology for the aircraft. And then Airbus is currently developing, and we hope by our aircraft, a commercial commercial deal. Okay. And we think this is the way of bring aviation to the industry to be, because there is money, yeah, but there is an important side, and this is, as we said in the introduction, this is a greener future for us, and maybe in 50 years this technology will be current, and everybody will take this eco-climb to reach the sky, as you say.
When you consider the loads, when you look at because we're talking about a larger aircraft as compared to a fighter, and the system that you would need to be able to slingshot it into the air. Have you considered the economic impacts on that? Would it be something that would be in the tarmac, or would it be an auxiliary system that's on, per se, on the wheels? Is it some other type? Is it a rocket? What is it? How would you?
About the EcoClimb, we write more about EcoClimb into the report, can check, but this is actually the plan to put TGV, train in French, electromagnetic motor. So this is totally independent of the aircraft. The catapult itself is a vehicle on the runway, yeah. And then we have two choices to develop this technology. This is the step Airbus work, actually. We can put these electromagnetic motors in the craft and just put the craft on the catapult to send it, or put directly on the track of the runway the catapult, and another source of energy will load this with purpose reduce the job, the effectively energy they need to go. And with our aircraft, is it big? You say that there is a big cargo, and with all the work we could develop in collaboration with Airbus, make it easier for the commercial line and improve the technology simply.
Last question.
Victor wants to add something.
Okay. Of course, we talk about the great of this thing, but there's also economic advantage because we are talking to the airport in Montreal and London. Of course, it's two big airports, and it's not only for our plane. This installation is can be used by other planes in the future. In 10 years, it's a
big deal.
Big deal. So big deal. Yeah. So economically, it's viable. We think about ecology, but there's also money there.
We have the question for one last question, yes.
If you allow me, since I'm with Bombardier, I'm very pleased to see. Yes, it's really interesting concept, and I really want to thank you for having a thought put in this. And specifically that I see on your pie chart you have an interestingly balanced distribution of the fuel burn improvement, so you don't rely like 30% or 50% on one source. So this is really great. And some of the ideas, and we bring even back to our engineers at my point. But as a drug and then as a member, I'd really like to see the operational cost. And given just picking one example that you mentioned a couple of times, the electric taxi. But did you know that the break even for having an electric taxi is having at least 3 cycles a day, given the weight penalty? So how much do you think this aircraft are going to go back and forth from London to Montreal a day?
Currently, no, I don't have the number, right? But I know the test and it's actually working with companies, I say. And this company gave numbers to develop more efficiency the technology of the wheel tug. And we know it because we are really into the information, the news about wheel tug. And they want to develop more of the economic side. Because there is the fuel. When you take off a plane, the fuel is expensive, right? Where in 2025, this is expensive, more than today. And so the electric solution could be really more viable. I don't have the numbers of the break-even, right? But in the development of this concept, this aircraft, we will totally not have the time, I can't say that, but we will think about it, we'll consider it, and this technology, we think this is the proper technology for the taxi and the more economic.
Thank you guys for your attention and your very